So this is Team 10, and here is our presentation for the EECS568 or RAW530. And our topic is the post-graph optimization for object tracking with visual-tactile perception. Our motivation is based on an open source project called Neural Fields. Since Neural Fields demonstrates phenomenal capability in object tracking, so we decided to look into it and try to make some optimizations based on it. We found that the SLAM backend in Neural Fields has certain limitations. Uh, for example, it can face a high chance of failure in the first few seconds due to a lack of SDF information, and it can also accumulate drift in post due to the lack of tactile information or visual failure due to occlusion and lighting. So we propose two solutions. The first one is the global registration and feature metric registration, which is also called the FMR. So I will first introduce the background of the neural fields. We will use two sets of sensors. The first one is the RGBD camera, which is set globally, and the second set is the vision-based touch sensors, which is implemented on each finger of the robotic arms. And for the first RGBD camera data, it will be sent to the segment anything part, and the depth information will be extracted from that. And for the second, the vision-based touch sensors, the data from it will go through a tactile transformer, and the tactile depths and the contact patches will be extracted. Then these two sets of data will be transferred into the backend of the system. In it, the neural field will sampling from vision and touch information, and the keyframes will be further transformed will be further transferred into the object model. And then my team members will also introduce how the post-graph optimizations works.
Based on neural fields architecture, we know that the front end converts vision and tactile RGB images to segmented depths, as is shown on this image, and the back end took depth and sensor poses from the front end to build object model online. First, we should perform point sampling from visual tactile depth images and alternatively perform optimization on pose and shape. So for efficiency, a bank of keyframes is maintained over time. The objective of post-graph optimization is to find the pose with minimum loss with regard to segmented depths and the frozen SDF. The loss function has three main components: the SDF loss, regularization loss, and point cloud registration loss. The optimization is performed using a Levenberg market optimization using the CSIS library. Uh, this optimization is better than Gauss-Newton or gradient descent because it is a second-order solver that can handle non-convex loss landscapes and has faster convergence. So central to the optimization is the SDF loss, which minimizes the distance between sensor sample points and the neural implicit surface by transforming points into the object's canonical coordinate system. To ensure temporal smoothness, regularization loss penalizes abrupt pose change between consecutive frames. Complementing these, the point cloud registration loss enforces global geometric consistency by aligning the transformed object model with observed scene points. Based on our experiment, we found that the ICP registration in the paper has low accuracy and affects pose estimation accuracy significantly. So we implemented global restriction and feature metric registration to increase the accuracy.
Let's start with a quick recap of point-to-point ICP. The goal is to estimate a rigid transform between two partially overlapping point clouds by minimizing the distance between each source point and its nearest neighbor. Each iteration involves a nearest neighbor search followed by an SVD-based alignment. When there is sufficient overlap, around 40%, and small initial error, ICP converges quickly. However, it's highly sensitive to noise, sparsity, or small overlap, and often gets stuck in local minima. To improve robustness, we introduce a global alignment step before local SAP. After voxel downsampling, we compute FPFH descriptors and use the RANSIC to find the coarse alignment in descriptor space, which is then refined using standard ICP. This pipeline significantly increases the capture range, handling up to 25 degrees of rotation or 50 millimeters translation error, but still struggles when overlap is very small or when many outliers are present. A feature metric registration takes a different approach. Instead of comparing of raw coordinates, it uses a neural network encoder to embed points into a layered feature space. We then optimize the transform so that the features match, not just positions. Using Leverberg Marquardt for optimization, FMR is robust to noise outliers and even low overlap, as little as 50%. It also allows us to inject category level priors, which is especially useful in Visuo-tactile slang. The trade-off is a need for a pre-trained network and GPU inference, but it provides the most stable performance in challenging scenarios. Then let my teammate give the result.
So this is our result, and first we compare the result of the different point cloud scenes. So as shown on the figures, so the SAP will get a very poor performance, and the global regularization will maybe a better performance. But for the best performance is FMR. This is showing that the FMR is in a good performance under challenging conditions with partial overlaps and noise. So after that, we compare the track error between three methods. Tracking error is computed as the root mean squared error between estimated and ground truth poles over the sequence. So showing on the plot, so the FMR gets a very brilliant performance, and we can see the ICP also gets a poor performance. And for the last part, we visualize the three registration approaches. The visualization highlights the difference in transformation. So as we can see, the SAP has low performance, and the global regression and the FMR yield smoother, more robust, and more precious results. And a key limitation arises from using the ADD metric for post-error evaluation, which fails to account for symmetry-induced ambiguous object. So our future efforts will explore color-augmented point cloud registration methods to resolve such some symmetry ambiguous by leveraging texture or chromatic filters. So this is our project. That's all. Thank you.